Good morning, everyone. My name is Jingbo from GraphAr team, Alibaba's group. The topic of my presentation today is GraphAR, unlocking efficient graph analytics in data lakes. GraphAR is an open source project and now is in Apache Incubator. Here's today's roadmap. We'll start with some background, and then I will introduce the labeled property graph representations in GraphAR. And then I will cover our optimizations of neighbor retrieval and label filtering, which are two fundamental graph operations. Finally, I will share some evaluation results and conclude. There are already many powerful graph processing systems. I've listed a few examples here, like TUC, Kuzu, GraphFriends, GraphScope, and HugeGraph. They perform very well on graph workloads, supporting tasks like querying, analytics, and other types of graph processing. However, there's a key question. If most of the data still lives in the data lake, how can we leverage these graph systems directly to perform graph analytics? In data lakes, graph queries or analytics often rely on a label property graph model, in which vertices and edges may carry labels and properties. While the model is expressive, existing storage in data lakes, mostly tabular formats, they doesn't naturally capture these semantics. The columnar formats like Parquet excel at storing individual tables, but they fall short in representing the complex relationships and semantics across table. They lack a native spot for graph-specific operations. This figure shows execution workflow of the query on tabular formats. You may see three tables, and if you want to answer the server query shown as this below, you may need to join these tables and do some joins between the tables and then do the selection. We think that this method is inefficient. So we identify three main challenges when querying a graph or do graph analytics on data lakes. The first challenge is that there is no standardized way to encapsulate labeled property graph within the existing data lake architecture. Existing tabular formats fall short of capturing graph semantics. The second challenge is the foundational operation of graph queries, like neighbor retrieval might require multiple joins in tabular formats, significantly impacting performance. The third challenge is label filtering, another essential graph-specific operation. It also introduces inefficiency due to the lack of native support in kernel formats. GraphAR addresses the first challenge by introducing a structured data layout. First, all of the metadata is described in YAML, and the schema of the labeled property graph is defined in this YAML. For example, in the YAML file shown on the left, you can see the graph name and path prefix and the definition of the vertices and edges in this YAML. And then it has a set of payload files. Parquet is utilized as the payload files as the payload file format for storing the data in the physical storage. At the conceptual level, we also have the vertex table and edge table. In the vertex table, it can reconstruct it from the payload files and together with the metadata YAML. It may include the internal IDs, labels, and property columns, and stored in the and partitioned in the multiple physical Parquet tables. For edge tables, GraphAR sort edges by source and destination IDs and introduce an auxiliary offset index. This index enables retrieval patterns similar to CSR and CSC format, which is widely used in graph engines. Eventually, GraphAR makes Parquet behavior like a graph native store. For neighbor retrieval, GraphAR use a method called page aligned collection, or PAC for short, to store the neighbor IDs compactly. This makes the fetching neighbors of a vertex much faster and more predictable. In this example, if we want to get the neighbors of the vertex 0, first we get a PAC for neighbors of the person vertex 0. And then our bit set representation will be used to facilitate the selection pushdown of vertex properties or labels. In this example, with the bit set representation, you can only just fetch the values with the non-zero bits in the Parquet files. Label filtering is another key operation. GraphAR encodes labels using round length encoding. This transfer or converts the binary representations of a label into an interval-based structure. So for simple conditions to filter vertices with or without a specific label, we can select all odd or even intervals based on the filtering condition and the initial value. For complex condition filtering, to handle conditions with multiple labels, it involves our merge-based algorithm to evaluate each interval. And if you want to select some combination of the label filtering and just pick the intervals from the merged array. To validate GraphAR, we conducted a series of evaluations. This is some micro benchmarks. For neighbor retrieval, GraphAR achieves on average more than 4,000 times faster performance. And for complex condition filtering, it delivers over 14 times faster results compared to existing approach. When integrated with GraphScope, GraphAR improves the graph loading by near 5 times and query execution by 2.4 times faster. This demonstrates that GraphAR is not just a standalone idea, but a practical enhancement for existing graph systems. To conclude, GraphAR is an efficient and specialized storage scheme for graph data in data lakes. And the graph organization with the meta data management enables a complete expression of labeled property graph semantics. The specialized optimization technologies enhance performance in label retrieval and label filtering. And the GraphAR achieves a substantial speed gains in label retrieval, label filtering, and end-to-end workloads. And it demonstrates the potential for seamless integration of GraphAR into existing graph systems. At last, I'd like to introduce the community and our ongoing work. Last week, we just released a new version with a stabilized API of Java SDK. And it also has some performance enhancement. And we are going to integrate GraphAR into some other graph systems. GraphScope is done, and we are developing a Kuzu extension to read the data from GraphAR, and also implement the support for GraphFriend. Here is a picture cited from the blog of a PMCC member of the GraphAR, and we are working on this to to develop a GraphAR as a bridge of the data lakes and graph analytic systems. Thank you. And this work also has been published on LDB 2025 named GraphAR, efficient storage scheme for graph data in data lakes. And it open sourced at this URL and is an incubator project. Thank you.